Welcome! Today, we're diving into the element that, quite literally, builds our world, carbon. I mean, it's in the food we eat, the fuel for our cars, it's just everywhere. But here's the crazy part. It's also super rare. So how is that even possible? Well, we're about to find out. All right, let's kick things off with a big question. If I asked you what the most important element for life is, you might say oxygen, right? Or maybe hydrogen. And yeah, they're essential. But the real unsung hero, the master architect of it all, is carbon. And the reason why is this amazing paradox, this puzzle of scarcity versus abundance. So get this, 0.02%. That tiny, tiny number, that's all the carbon you'll find in the entire Earth's crust. It's just locked away in minerals, coal, and oil. For an element that's supposed to be the foundation of everything, it's surprisingly rare. And if you thought that was a small number, look at this one. That's how much carbon, in the form of carbon dioxide, is in our whole atmosphere. I mean, think about it. The element that forms the basis for all living things, and there's just hardly any of it easily available. It's a real puzzle, right? So that leads us right to the big mystery we're trying to solve today. How on earth does this incredibly rare element become the backbone for literally millions of different compounds? The secret, it turns out, is all in how it's built, right down at the atomic level. Okay, so the first piece of the puzzle, the first clue to carbon's incredible power, isn't about taking or giving. It's all about sharing. You could say carbon is the ultimate team player at the atomic level. See, most elements form bonds in one of two ways. They either give away their electrons or they steal them from someone else. That's an ionic bond. But carbon, it's different. It has 4 electrons in its outer shell, and getting rid of them or grabbing 4 more is just too much work. So it does something much smarter. It shares. And this sharing creates these super strong and stable connections we call covalent bonds. The most basic way this works is a single bond. It's pretty straightforward. 2 atoms each put 1 electron into the pot, and that shared pair holds them together. It's kind of like atomic glue. But why stop at 1 pair, right? Atoms can get a little more generous. Take oxygen, for example. Here, each atom shares 2 of its electrons, forming what we call a double bond. And you can probably guess, that's an even stronger connection. And then you have this, the triple bond. We're talking 3 shared pairs of electrons. This creates an incredibly powerful connection, one of the strongest you'll find in nature. And here's the kicker. Carbon can form all 3 of these, single, double, and triple bonds. That is a huge part of what makes it so incredibly versatile. So this knack for sharing electrons, it basically gives carbon 2 incredible properties. I like to think of them as its superpowers, and they're what allow it to build all the amazing, complex molecules that make up life as we know it. First up, superpower number 1, tetravalency. It's a fancy word, but it just means carbon can form 4 bonds at the same time. Think about it. It's like a tiny little Lego brick with connectors on all 4 sides. This lets it build out in every direction, creating these amazing, complex 3D structures. Okay, superpower number 2, and this one is the real game changer. It's called catenation. All that means is that carbon atoms are amazing at linking up with other carbon atoms. They can form these long, super stable chains. A few other elements can do this a little bit, but nobody, and I mean nobody, does it like carbon. And this whole chain-building journey starts with something really simple, methane. It's just one single carbon atom bonded to 4 hydrogens. You probably know it as the main ingredient in natural gas. But then we can add another carbon. Now we've got ethane. You can see the chain starting to form right here. 2 carbon atoms are linked up, and all their other available bonds are holding on to hydrogens. Add 1 more, and what do you get? Propane. Yeah, the stuff that powers your barbecue. And this is the whole point. This ability to just keep adding to the chain, to form these long, stable links, is what allows for the mind-boggling variety of molecules that make up, well, us. These chains can keep going, forming everything from simple fuels to plastics to the proteins in your body. So you take those 2 superpowers together, the ability to bond with 4 things at once and the ability to link up with itself, and suddenly carbon becomes the ultimate molecular architect. It can create a nearly infinite library of blueprints for molecules. For instance, it can build nice, simple, straight chains. This right here is butane. Its straightforward, orderly structure is what makes it a great, stable fuel for things like lighters. But here's where it gets really cool.
You can take the exact same ingredients, the same number of carbon and hydrogen atoms, and just arrange them differently. So instead of a straight chain, you get this branched one. They have the exact same chemical formula, but they're completely different compounds with different properties. We call these structural isomers. It's like having the same Lego bricks but building two different things.
And it doesn't just stop with chains. Oh no. Carbon can also loop back around on itself and form these incredibly stable rings. This structure, cyclohexane, is a great example. This opens up a whole new world of possibilities for building even more complex molecules.
Okay, so all this talk about chains and branches and rings, what does it actually mean in our daily lives? Well, to see carbon's genius at work, you don't have to look any further than a bar of soap.
The reason soap works is all down to its really clever carbon-based design. See, every soap molecule has two parts. It's got this long tail made of a carbon chain, and that part is hydrophobic. It hates water, but it loves oil and grease. Then it's got this other end, the head, that's hydrophilic. It absolutely loves water. This split personality is the secret to how it cleans.
So when you wash your hands, here's what happens. The soap molecules swarm the oily dirt. Their oil-loving tails all dive into the grime, grabbing onto it. They surround it, forming this little cage called a micelle, with all the dirt trapped inside. Meanwhile, the water-loving heads are all on the outside, facing the water. So when you rinse, the water just grabs onto those heads and pulls the entire dirt-filled package right down the drain. It's genius, really. A perfect piece of molecular engineering.
And there you have it. That's how a pretty rare element becomes the master architect of, well, everything. It all comes down to a few simple rules about sharing and connecting, which give rise to the incredible complexity of life. From the fuel in our cars to the very DNA in our cells. It really makes you think, doesn't it? What will we decide to build with it next?